We'll move now to the third speaker for this session, Arafat Mahmood from City University of London. Arafat is a Marie Curie Research Fellow at the Department of Mechanical Engineering in the City University of London. He was awarded the Sensor for Diabetes project from the European Commission under the Marie Sklodowsky-Curie Individual Fellowships, and is working on gas sensor technology for detection of diabetes from exhaled breath. He obtained his PhD from the University of Malaya on gas sensors technology using metal oxide nanostructures. He has also worked as a review editor in reference module in materials science and materials engineering, and currently he is the reviewer of various reputed journals. And in his talk, he will share with us insights regarding metal oxide-based chemoresistive sensors for detecting and management of diabetes from exhaled breath. Please, Arafat.
Good afternoon, everyone, and welcome to my presentation. The title of my presentation is Metal Oxide-based Chemoresistive Sensors for Detecting and Management of Diabetes from Exhaled Breath. I am Arafat from City University of London and presenting on behalf of my research group. This presentation is a review-based work on the current understanding of breath analysis for detecting diabetes and the feasibility of chemoresistive sensor for detecting diabetes from exhaled breath. In this presentation, at first I will provide the background of this study. The main presentation is divided into two groups. In the part 1, I will provide the clinical findings of breath analysis, and in part 2, I will provide the progress in developing breath analyzing sensor for detecting diabetes. Finally, I will summarize the findings. Diabetes and related illness is a growing problem worldwide. According to the International Diabetes Federation, in 2019, worldwide about 463 million people have diabetes. In addition, there are 1.1 million diabetic children. It is estimated that by 2045, there will be more than 700 billion diabetic patients. In the recent time, each year about 4 million people die due to diabetes. In 2019, the cost of diabetes management was 760 billion USD worldwide. It is predicted that in 2045, this cost will reach to 845 billion USD. Worldwide governments are struggling to cover the cost of diabetes care and related financial burden. Normally, blood glucose and glycohemoglobin levels is monitored for diabetes management. American Diabetes Association recommended to monitor blood glucose at least 3 times in a day. Daily self-monitoring of blood glucose is a problem for many patients, particularly children. A big number of patients regularly forget to monitor blood glucose. This is also expensive, unpractical, fearful, and painful, so there is a high demand for non-invasive, continuous, portable, cost-effective, and quick detection devices for monitoring and management of blood glucose. In theory, it is possible to detect and monitor diabetes from the exhaled breath. In clinical settings, researchers have tested different breath gases and quantified them using expensive and sophisticated spectroscopic techniques. However, these techniques are not suitable for on-site use due to their non-portability, complexity in sample preparation, having bulk size, and high cost. As alternatives, a variety of methods have been developed. Out of those, chemoresistive sensors are an adaptive solution. Such sensors are simple, provide high miniaturization, consume low power, and require low production cost. However, such sensors must be capable of detecting breath gases in parts per million to parts per trillion levels in the presence of complex mixture of human breath. In addition, the sensor should be robust, easy to fabricate, portable, cheap, and non-toxic. So, to fabricate an effective breath analyzing sensor for detecting diabetes, the knowledge from the clinical studies and sensor communities should be masked. However, some research gap and ambiguities are seen in the approaches between these scientific communities. This presentation bridges the knowledge obtained from the clinical studies and sensor communities. The part 1 of this study focuses on the knowledge from clinical studies. At first, we need to understand the typical breath composition. Typically, humans inhale breath from the ambient. Some external factors and metabolic activities also contribute to breath. The exhaled breath constituents come from the endogenous and exogenous sources. It also contains volatile organic compounds which originates from ambient and metabolic activities. Due to the prevalence of diseases, the composition of VOCs is changed, which can be used to identify diseases. It is a common and popular wisdom that breath acetone is a biomarker for diabetes. When someone eats food, it converts to glucose. That glucose is carried to the cell by insulin and releases energy. However, if someone has lack of insulin or insulin resistance due to diabetes, this process cannot take place and body suffers a crisis of energy. To overcome this energy crisis, liver breaks down fats and produces some ketone bodies, including acetone. These ketone bodies accumulated in the blood and exerted in breath. Out of those ketone bodies, acetone is more volatile and more detectable in the exhaled breath. However, this symptom typically occur during diabetic ketoacidosis. Some factors also contribute to acetone concentrations in breath. So, acetone is not a reliable biomarker for diabetes. So, researchers investigated other biomarkers such as methanol, ethanol, propane, methyl nitrate, 2-pentyl nitrate, isoprene, ethylbenzene, xylene, glucose, carbon dioxide, and carbon monoxide using various sophisticated systems such as gas chromatography and mass spectroscopy. Out of all these gases, it is seen that acetone, isoprene, methyl nitrate, and carbon monoxide can be considered reliable biomarker for diabetes. It is seen that the concentration of acetone increases up to 10 times. On the other hand, isoprene, methyl nitrate, and carbon monoxide is almost doubled in diabetic breath. There are some limitations in clinical studies. Most of the studies relying on acetone for diabetes monitoring, and the correlation between breath acetone and blood glucose level is ignored. Acetone probably a biomarker for diabetic ketoacidosis. So, as a suggestion, integrated study focusing few biomarkers is required. To utilize the knowledge from clinical studies for developing a breath analyzing sensor, we should learn the mechanism of gas sensing using chemiresistive sensors. Though the mechanism could be quite complex, in short, it can be said that the resistance of the material in chemiresistive sensor is changed in the presence of certain gases. The response of the sensor is measured from the ratio of the resistance in ambient and target environment. To fabricate the sensor device, the gas sensing materials are deposited on a flat or tube-shaped substrate and connected with appropriate electrical circuit to monitor the resistance. Such setups are utilized for developing breath analyzing sensors for detecting diabetes. However, most of the researchers focus on only detecting acetone in exhaled breath. Researchers also tried to improve the performance of the sensor by adopting various techniques, which is discussed in the following slides. For example, some researchers increases the surface area of the gas sensing materials by developing novel nanostructures, such as nanoparticles or flower-like structures. It is seen that such structures are capable of detecting low concentration of acetone with higher response due to having higher surface for gas absorption and desorption. Some researchers used heterostructures to detect acetone in exhaled breath. For example, graphene oxide tin oxide heterostructures shows response of 33 towards 5 ppm of acetone, which further increases to 60 when graphene oxide, tin oxide, titanium oxide ternary heterostructure is used. Again, some researchers loaded ceramic or metallic nanoparticles on gas sensing materials to improve the performance. And it is seen that the response of the sensor is improved a lot with the loading nanoparticles. For example, loading of titanium dioxide nanoparticles on indium oxide nanowires or platinum nanoparticles on zinc oxide nanowires significantly improve the response towards acetone. Similar to loading nanoparticles on the gas sensing materials, addition of various dopants such as aluminum, cobalt, and silicon in the gas sensing materials also improve the acetone detection capabilities. Some researchers also combine the approaches. For example, loading of palladium oxide nanoparticles on cobalt oxide indium oxide heterostructure, which is in a shape of a hollow sphere, improves the acetone sensing response more than 4 times compared with bare indium oxide hollow spheres. There are some limitations in the investigation of diabetes detection using breath analyzing sensors. Most of the study focuses on acetone detection. A combined study focusing on other VOCs are required. The investigation should focus the practical situation mimicking the actual breath compositions. The sensor should be tested in parts per trillion level concentrations. To obtain all this, a sensor array could be beneficial and several gas sensing principles can be combined. From this study, we can conclude that in theory, diabetes can be monitored using breath analysis. Most of the researchers focus on acetone detection for detecting diabetes from breath. However, acetone is more likely to be a biomarker for diabetic ketoacidosis. Besides acetone, other biomarkers such as isoprene, methyl nitrate, and carbon monoxide are promising VOCs for detecting diabetes. The concentration of these VOCs is usually in parts per million to parts per trillion level. Chemiresistive sensors are capable of detecting these gases, and it is further improved by adopting various techniques. So, chemiresistive sensors are potential candidates for detecting diabetes from exhaled breath. Before finishing this presentation, I would like to acknowledge the Marie Curie Individual Fellowship from European Commission Research Executive Agency. Thank you.
Well, thank you very much, Arafat. Again, diabetes and acetone, very, very intriguing and exciting topic, mainly that the metabolic pathway of diabetes has been very well characterized, I would say, in link of VOCs, as you have said. We have some questions here, but I'd like to start with one of mine, if you don't mind. The diagnosis of diabetes actually typically done by measuring blood glucose and at specific timing or at specific conditions. So are you looking for VOCs that actually represent blood glucose, or you're looking for a combination, like you've said, that allows the detection of diabetes regardless of what or how balanced the blood glucose levels are?
Thank you for this question. Actually, basically, I am, sensor community, so I have less idea about, your clinical studies. But yeah, if we know that the exact condition that how the acetone concentration varies in relation with the blood glucose, we try to make the sensor that can capable of detecting a specific amount of acetone so that they can detect diabetes. Yeah.
Thank you for that. We have a question from Paula. She thanks you for the talk, and she asked regarding the chemoresistive gas sensor. How is the sensor tested in simulated human breath with acetone?
Okay. Actually, we will do. We'll simulate the, human breath in some kind of chamber, and we'll put our sensors inside the chamber, and we'll try to mimic that how actually human breath is exerted, and we'll see the behavior of the sensor in terms of resistance and their photonic behaviors, how it is changes in presence of normal breath, normal synthetic breath, and normal, diabetic breath. And then from that difference in terms of resistance, we will understand that, diabetic, yeah, diabetic breath.
Okay, and other than breath, do you produce any different mixtures of VOCs plus humidity, for example, to simulate breath for training purposes, testing, development of the sensors themselves, or you go directly and test with breath typically?
Basically, for this moment, we are not focusing any other diseases or any other thing. We are just trying to focus on diabetic breath. Yeah.
Thank you very much. There's a question from Scott. Scott's asking about the production cost of a sensor array. Do you have any vision in the future about how much that might cost as a product?
Okay, actually, the chemoresistive sensors are quite cheap because production of metal oxide nanostructure is very cheap process, and it is also scalable. The main cost actually comes from the substrate and the electrodes, which is typically gold wire or something like that. But if we buy for laboratory scale, it may cost, for example, I can say like 5 to 10 pounds. Yeah. But when we go like commercial production, basically it will be much more cheaper.
And question here from Nathan, how real time are these measurements, and what is the lag between the detection of VOCs and the blood glucose? Have you tested the provision of glucose and monitoring different VOCs, for example?
Okay, as I mentioned earlier, that actually we are focusing on the sensor fabrication. We are not the clinical community, right? So we are actually depending on the data that we find in the literatures. Okay, but however, our initial study shows that a sensor can detect diabetes within maybe 10 to 20 seconds, something like that. Yeah. So the response times of the sensor when you blow the gas, it typically just less than half minute. Yeah.
Thank you very much, Arafat, for presenting your research, the development of the sensors.